this problem, number 29, seems to be a lot of difficulty for a couple things. One, there's all sorts of letters all over the place, which freak people out. The other thing is the x and the y are actually not what we're going to 0 on, right? It's p that's really the variable here, right? P is approaching 0. So that makes this a little weirder in that sense. Let's try plugging in 0 for p. We would have x to the 0, that's 1. We'd have y to the 0, that's 1. So inside here we just get a times 1 plus b times 1. That's just a plus b. So we have the natural log of a plus b. But the problem specifically told us a plus b is 1. So if that's 1, the natural log of 1 is in fact 0. Denominator, p goes to 0, that's going to 0. So we have the 0 over 0 means we can use L'Hopital's rule. So, using L'Hopital's rule, we have the limit as p approaches 0. Okay, so derivative of a natural log is 1 over the entire inside, ax to the p plus by to the p. Chain rule times the derivative of the inside. Now this gets a little tricky because, remember, p is the variable, not x. This is not a power function. This is, in fact, exponential. P is the variable. So what is the derivative of an exponential? It's the exponential times the natural log of the base. In this case, the base is the x. So natural log of x. Same thing for the second term there. It's by to the p times the natural log of the base. This case, the base is y. Okay, so that's the derivative of the numerator. Divided by derivative of p, well, that's going to be 1. Remember, p is our variable. So maybe just a quick rewrite here. So dividing by 1, don't worry about that. In the top we've got 1 times all of this, so we're going to have ax to the p times the natural log of x plus by to the p times the natural log of y all over ax to the p plus by to the p. Now let's try to plug p in, or 0 in for p. So we would have an x to the 0, a y to the 0 there. So those become 1s. So we'd have a natural log x plus b natural log y. A natural log x plus b natural log y. Oops, that should be a y. And in the denominator, same thing. 0 in for the p's. We're going to get just a times 1 plus b times 1. So that just gives us a plus b. And again, if you remember, the problem told us that a plus b was given to be 1. And so plugging that value in, that means the denominator is 1. We get a natural log x plus b natural log y. And so that's it. That's the answer to part A. Now we use this in part B. So for part B we have this limit that it's asking for. This is going to be similar to our idea of logarithmic differentiation. Okay, so you know we want to consider this whole thing here. Think of this as, you know, the limit then as p goes to 0. This is the same as e to the natural log of this whole thing. I'm trying to avoid writing the whole thing. That whole thing. E to the natural log of the whole thing. You know, why do we want to think of it that way? Well, that means we can rewrite this then. Right? I guess I'm going to write it anyways. So we're going to have e to the natural log of ax to the p plus by to the p. Okay, that's to the power of 1 over p, but let's take that power 1 over p, property of log says write it up front, 1 over p. And so really, you know, e is just constant, so really this is e to the limit as p goes to 0 of this stuff. Now I'm going to rewrite it this way, the natural log of ax to the p plus by to the p, good timing, all over p, and this limit that I've just written up top here is exactly part A. So you can plug the answer to part A in there and it's e to that.